Welcome back to some more trig in chapter 14, the graphing chapter. Today's targets will be: I can calculate the 5 values of trig functions given the value of one trig function for a given domain, and I can simplify trigonometric expressions. Trigonometric identities. You are going to want to pause this right now and copy down all these identities, because I'm going to move on to the next slide here really quickly. So pause it, get all these copied down. They're also in your note, or in your book, excuse me, on page 924. So you can get them from there as well, but you want to have them in your notes. So pause it and copy them down before you move on. Okay. Given the cosine of theta equals -3/4, and theta is in the interval pi to 3 pi over 2, find the value of the other 5 trig functions. Well, we remember our definitions of cosine and sine and the coordinate plane. And you're going to put all that together to find the other 5 trig function values. So if we're between pi and 3 pi over 2, pi is the equivalent of 180. 3 pi over 2 is the equivalent of 270 degrees. You can look at using a circle for that. That means we're in here somewhere. We're in this quadrant 3. That's what this means. So that an interval or domain they give you is just telling you which quadrant are you in, 1, 2, 3, or 4. So cosine of -3 over 4, well, that's, if you look at cosine, the definition of that is x over y, or adjacent over hypotenuse. So, excuse me, x over r, not x over y. X over r. So we can use that information to kind of label some sides of a right triangle. So if we're in quadrant 3, then that must mean the x value is negative, so that's -3. And our hypotenuse is 4. So we have to find y. How do we find y? -5. How are we going to find y? We're going to use the Pythagorean theorem. X squared plus y squared equals r squared. -3 squared plus y squared equals 4 squared. 9 plus y squared equals 16. Y squared equals 5. Or y, oops, not 5, 7. Y squared equals 7. 16 minus 9 is 7. 5. So y is the square root of 7. So now that we know that side, we can find the other trig function values. We can find them all. Sine of theta, cosine of theta, we already know that is -3/4. Tangent of theta, and of course we can do the reciprocal functions, cosecant, secant, and cotangent. So we know that sine is defined by y over r. Y is the square root of 7, r is 4. We know that tangent is defined by y over x, which is negative square root of 7 over negative square root of 3. Why is it negative square root of 7, by the way? I didn't label it as that up here. But why? It should be negative square root of 7. Why is it negative? Because we're in quadrant 3. In quadrant 3, and we're going down, it's going to be negative. And we know that cosine is negative in that quadrant. So that tells us that this has to be, the square root of 7 has to be negative because we're in quadrant 3. Okay? Put that on there. So negative square root of 3 over -3 is just positive square root, excuse me, negative square root of 7 over negative square root of 3 is square root of 7 over 3. So I forgot to label that negative sign on there, but obviously it makes sense for going down. It has to be a negative square root of 7. Cosecant, to finish it off, once we have those three, we just flip these. We have, if this would be 4 over negative square root of 7, we multiply by square root of 7 on the top and on the bottom to get 4 square roots of 7 over 7, and obviously this is still negative. Secant would be the flip of negative 4 over 3, so negative, should flip a negative 3 over 4, the reciprocal, so negative 4 over 3. And cotangent, that would be the reciprocal of square root of 7 over 3, so 3 over the square root of 7, which is square root, or 3 square roots of 7 over 7. Okay, so that makes sense. In quadrant 3, tangent and cotangent are the only positive functions, so they're our only positive ones here. All students take calculus, you'll do that. And hopefully that makes sense with the negative square root of 7, why it had to be negative. So we're in quadrant 3, and we're going down. So because we're in quadrant 3, this is a negative square root of 7. Okay, so the other part of this lesson is simplifying. Tomorrow we're going to do verifying, which is like proofs. But we're going to kind of baby step our way there. Today we're going to do the simplifying. So we want to take this expression 1 over the sine of pi over 2 minus theta times cotangent of theta, and we want to simplify it. So if you're simplifying it, generally you're condensing it. You're making it smaller. So remember all those identities that we wrote down at the beginning of the lesson? We're going to try and use some of these. Okay? So I'm not going to tell you there's always one right way or one wrong way, but whenever you see a tangent or cotangent function in there, along with sine or cosine, it's always a good idea to try one of these tangent and cotangent identities. And we can see that cotangent equals cosine over sine. So these identities that we're given, we can assume are true. Anytime you're given an identity, and anytime we prove that something equals something else, we can use that as well. But we're given these identities. We know they are true. We can manipulate them. We can rewrite them. If I wanted to solve one of these identities, for instance, for sine of theta is tangent times cosine. I could rewrite it and use it however I want. In this case, we're just going to use the identity as it is. We're going to take out cotangent, and we're going to put in cosine of theta over sine of theta. So all we did is we swapped cotangent for cosine over sine. You say, well, that really hasn't done anything yet. But then I see I have the sine of theta, or pi over 2 minus theta. So let's see if we have something up here that might be useful. And I think, in fact, we do. It says sine of theta, or excuse me, sine of pi over 2 minus theta is just equal to cosine. So I'm going to swap out sine of pi over 2 for cosine. I'm going to put that in over here. 1 over cosine of theta times cosine of theta over sine of theta. And why is that cool? Well, I've got a cosine of theta on the numerator and the denominator. And so they cancel out, and I end up with 1 over the sine of theta. And 1 over the sine of theta, I don't know that we need the identity for it, but if sine of theta is 1 over cosecant, we can solve this, and really these can flip-flop. So we can see that 1 over the sine is simply just cosecant. So this whole expression will simplify to just cosecant of theta. Okay, the negative cosine of x times the tangent of negative x. Well, I would say this is probably going to be a prime candidate for negative angle identities. Tangent of negative theta is just the opposite of the tangent of theta, so we can start there. Minus cosine of x times negative tangent of x. Well, a negative times a negative makes a positive, so this would be positive cosine times the tangent of x. And then we remember that the tangent of x is simply sine over cosine. This is really cosine over 1, technically, so we cancel that off, and then we end up with just the sine of x. So this expression simplifies to just sine of x. Okay, so I think we hit both targets. Make sure you have the notes down for tomorrow. We'll see you in class.